Okay, so in this lab video, you're going to see Thomas, Maggie, and Jada doing the different dilutions and wiping the sides of the cuvette. Thomas is doing that right now.
Write down the name, file name. Write any name.
Star.
Oh my gosh. That's it. I'm override.
Right, do like...
And then let's start too. Finish. Finish. Okay, good. You are having my voice, not your stock, but some other, so you're just gonna clear report.
Okay, so next we see Jada. She's doing our second dilution. She's wiping the sides of the cuvette and closing it carefully. We're naming our second dilution, and we're reading the graph and recording our values.
Oh, that one, okay. I know it now. Keep my mouse there, and it gives me X value. Oh, okay. Write down that value. Right, here you go.
Okay, so this is Maggie. She's doing the second.
Okay.
She's doing the first unknown.
Sorry.
And then we're also reading the graph right here and recording our values.
Because I'm normal.
That's not normal. It's being quiet and like communicating telepathically. They communicate with their minds.
I think it's Tilly. Read. It's reading. It's filming.
Sorry.
Hi, this is my segment on Beer-Lambert's law. It represents absorbance equals molar absorbidity times the path length times your concentration. Variable A, or absorbance, can be determined by looking at the top left corner of the program linked to the spectrophotometer. The epsilon variable represents molar absorptivity, which can be found by dividing absorbance divided by path length times concentration, or you can reference the graph to find the slope to find epsilon. Your B variable represents your path length, which is the amount of centimeters that the light passes through, which for our case was 1 centimeter. The next and final variable is C, which stands for our concentration sample. To find concentration, you can take your absorbance value and divide that by your path length times your molar absorptivity. Absorbance is directly proportional to concentration. The more concentrated a solution is, the more radiation gets absorbed, therefore the higher the absorbance. When using a spectrophotometer, it is very important to zero the machine using a blank cuvette. This is because the absorbance value will now be at 0 and will set a basis for the rest of the dilutions to be compared to.
Here's where we recorded our lab data, and we have the mass of the watch glass, the mass of the watch glass with the paper, and we'll use those masses to subtract from the original to find the mass of our dilutions. Below that we have the spectrophotometer data when you have our X and Y value. Here is our data from the spectrophotometer. Under red we have our 0, our dilution 1 through 3, our 2 randoms, and our pure. The more we diluted, the less our substances were able to absorb light, which is why our numbers are changing here.